Hey everyone, this is your friendly neighborhood math teacher, Mr. Bennett, back again with another lesson. Today we're talking about 9.3a, and as you can see at the top, our two learning targets. We're going to first look at the hypotheses for a significance test about a difference between two proportions, and then learning target number two, looking at the conditions and whether or not those are met for performing that significance test. So both developing the hypotheses as well as looking at the conditions necessary. So today's 9.3a activity, we're looking at, is yawning contagious? So the show Mythbusters, I don't know if you guys have seen this show, it's a little bit older now, but the show investigated a question. The brief recap was this: each subject was placed in a booth for an extended period of time and monitored by a hidden camera. 34 of those subjects were given a yawn seed by one of the experimenters. What that means is the experimenter yawned in their presence before leaving the room. The remaining 16 subjects were given no yawn seed. So the experimenter just walked them into the room and then walked out without yawning. So number one, draw an outline of this Mythbusters experiment, and I kind of get you started here. So first we have our 50 subjects, which then goes into random assignment. So they get randomly assigned into two groups. Group 1 and Group 2. Our Group 1 was the 34 subjects, and Group 2 was the 16. The 34 in Group 1 were given the yawn seed treatment, and Group 2 was given no yawn seed. And then ultimately, once we've given those treatments, we then come back together and compare the proportion of yawners. So did these people actually yawn? Number two says, here are the results. So were they given the yawn seed? Yes. And then did they ultimately end up yawning? Yes. Would be 10. If they were given the yawn seed but then did not yawn, that was 24. So I'll let you kind of look at the rest of that little table there. But our first directions say to call P1 the true proportion of yes yawn seed people who yawn. So I know that's a little confusing, but that means yes yawn seed, yes yawn. So that would be 10 out of those 34 people, which comes out to about a 0.29 as a decimal. So that's our P hat 1. And we're going to call P2 the true proportion of no yawn seed people who still yawned. So again, no yawn seed, still yawned, would be 4 out of 16, which is 0.25. So what is the difference in those two proportions? P hat 1 minus P hat 2? Well, 0.29 minus 0.25 is 0.04. So question 3, do the data provide some evidence, not necessarily convincing, but some evidence that yawning is contagious, and why? And at this point, we can say yes. People who were given the yawn seed yawned more often than those who were not given the yawn seed. right? And we can see that because our proportion's higher, right? Those who were had a higher proportion than those who were not. That 0.29 is bigger than 0.25. If our difference had been negative, right, then we would say that it was different, right? That we're actually not, or there is still some evidence, but in this case, that having no yawning is actually still contagious, which I think would be weird to see, to be honest, but that is a possibility. So number 4 says Adam Savage and Jamie Heineman, who are the co-hosts of Mythbusters, if you've never seen that, Adam and Jamie, they use these data to ultimately conclude that yawning is contagious. And so do we agree with that? Again, right, that was one sample. And so is that one sample enough evidence to actually make that conclusion? Even though it does provide some evidence, I don't think that would be enough to really be convincing evidence. And so in this case, no. A difference of only 0.04 doesn't seem like a big enough difference. And if it had been higher, right, if I had gotten, much, much, much higher, closer to 1, right, then I'd probably be like, wow, that's, pretty convincing there. But the fact that these percentages were so close together, yes, there was a small difference, but it wasn't very big. And at that point, it could have just happened purely by random chance. And this is from that random assignment, right? Those people just happen to be randomly assigned to those rooms, and that could have made all the difference, right? If we randomly assigned different people to those rooms, maybe they would have been more resistant to yawning, or something like that. And so that random assignment, right, if I had taken a bunch of samples, may have shown that really wasn't all that significant. And so we're going to look at that today. But that's the idea so far. So this would obviously work a little bit different if we were doing this in class. But through video, I'm just going to kind of walk you through this process. You can mimic me on your own if you want, or you can copy down kind of what I'm going to put here for this experiment. Either way, it's up to you. I don't really care what you do. These are your notes. But we're going to investigate whether those results are actually statistically significant, or could they have just been random. Okay, so question 4, what is the null hypothesis? So our null hypothesis is that P1 minus P2, the true proportions, are 0. And basically what we're saying here, right, is that P1 and P2 are the same, they're equal, which is another way of saying that yawning is not contagious. So we're going to assume that yawning is not contagious. Okay, so whether they had somebody yawn at them in the room before they left, or whether they just walked them in and then left, it wouldn't matter. Okay, so we're assuming it's not contagious. So it says the 50 people in the experiment are represented by cards. For this part, I'm actually going to share with you a Scratch code that I built for this, but I'll walk you through that. I'll show you that in the video here. It says a person is either a yawner or a non-yawner, no matter which treatment they are assigned. Step 5 says shuffle the 50 cards and put them into 2 piles. One group of 34 that gets the yawn seed. So somebody walks in with them, yawns, and then walks out. And then a group of 16 that does not get the yawn seed. Record the proportion of people who yawned, so specifically the ones who did yawn. And then we're going to do this 3 times. So hopefully this part won't take super long, but basically here's what we're going to do. Pull this up. Whoops. There we go. So hopefully this will work. So you'll see here in a second, I'm going to have 50 people. They're all designated as either yawners or not yawners. It's just a matter of where they get randomly assigned to. So they're either randomly going to get assigned to the yawn seed or the no yawn seed. And really what we're focused on is those first boxes underneath each list here that says the yawn seed yawns and then the no yawn seed yawn. Excuse me. So to make this work, if you want to try it yourself, all you have to do is click the green flag. It'll show you there's my 50 cards list. They get randomly assigned. And so we can see that the people who yawned in the yawn seed group was 8 out of 34. The proportion who who yawned but were not in the yawn seed group were 6 out of 16. And so we're going to go ahead and calculate those really quickly. I'm going to do that off screen, sorry, but just put that into your calculator. 8 divided by 34 gives me a 0.24 if we round up. Mine says 235, so we'll round up to 24. And then 6 out of 16 is 0.38. So to find the difference there, to do p hat 1 minus p hat 2, we had 0.24 minus 0.38, which is a negative 0.14. And then we're going to do that 3 times. So if you want to run your own 3, that's fine. I'm just going to continue to put these in so you can see them on my screen. And again, you can just follow along. So hit the green flag again. It resorts them. Our first group is going to be 12 out of 34. Our second group was 2 out of 16. So 12 out of 34 is a 0.35. Our 2 out of 16 is 0.13. 0.35 minus 0.13 is 0.22. And then trial number 3, run that one more time. And we get 11 out of 34. So that's going to be pretty close to what we just got. 3 out of 16, which again should be close to what we just got. So 11 out of 34 is 0.32. 3 out of 16 is 0.19. 0.32 minus 0.19 is 0.13. And then part 6 says to make a dot plot. So because we're not doing this all together, I'm going to kind of show you a way to simulate this. You can either do this on your own, or again, if you want to, pause the video and take a screenshot or whatever and just use mine, that's up to you. My guess is even if you do this on your own, you'll probably get something pretty similar. Even if it's not the exact same, you'll get something that is pretty close and would be close enough that it would still come out to be the same answer. So I'm going to go ahead and hide Notability for a minute. If you click on that link in number 6, it'll take you to a website that looks like this. The Rossmann-Chance Applet Collection, Analyzing Two-Way Tables. So all I'm going to do here, so I'm going to click on this button in the middle that says Show Shuffle Options. That pops that up. Okay. From there, I'm just going to it's going to run a simulation for me. And you can see that they've got blue and green people here that represent my successes and failures for Group A and Group B. Group A being the yawn treatment, Group B being the no yawn treatment. And I'm going to say that I want 50 shuffles. And then I'm going to hit shuffle. So there are my 50 simulations of doing what we just did. okay, having them sorting, randomly assigning them to groups, and then calculating all of this, and then finding those differences in proportions. So what I want you to do right now is recognize, okay, yeah, if we look at our chart here, it almost looks pretty normal, right? Maybe a little skewed right, but pretty normal. And then also, right, kind of in the middle is where our 0 is, if we look at our x-axis. And so what we can do here, the kind of cool thing about this is it says count samples greater than or equal to, and we're going to use that here because in our notes, we'll do the dot plot in just a second, we'll put that in. But number 7 says, what percent of the class's trials did the difference in proportions equal or exceed that 4%, right? Which is what the Mythbusters got. So basically, we're trying to look and see, was this ultimately statistically significant? And so what we're going to do is on our applet here, we're going to say, I want to know what was the number of samples that was greater than or equal to 0.04. That was our 4%, right? Where the difference was 4% or bigger. And if I hit count, I'm going to hide my keyboard again, sorry. Count, it will tell me. Okay, it'll kind of put the line in for me, and it'll tell you 24 out of 50 of them were for a percentage of 0.48 or 48%. So almost half of my samples had that number or bigger. Okay, so I'm going to go ahead and just zoom in here and take a screenshot. And I'm going to do some quick cropping just to get some of that out of the way. And we'll save that to photos, jump back in, go ahead and plop that down. Sorry guys. So there's our dot plot, and I already forgot the number. I'm sorry, 24 out of 50. Which was 0.48 or 48%. And so again, right, this red line here, kind of what it's looking at for us, this was the Mythbusters result, right, the 0.40, or sorry, 0.04. And so from that, right, 48%, which again, as a reminder, this number here is our p-value. What does this mean, right? We just found that there were 48% of those dots that were bigger than that 0.04. So remember, we can say this, assuming our null hypothesis is true, meaning yawning is not contagious. So if we assume that is true, there is a 0.48 probability, or you can say 48% chance, of getting a p hat 1 minus p hat 2 of 0.04 or greater purely by chance. So we're saying there's a 48% possibility, almost a 50-50 chance of just getting that number by pure randomness, like just random luck. And that's really high. And as we've kind of talked about through the last unit and into this unit, what conclusion can we make, right? That all comes down to the fact that because 0.48 is much bigger than that 5%, right? 48% is much bigger than 5%. We fail to reject our null hypothesis and do not have convincing evidence that yawning is contagious. And again, this is for me, even personally, right, kind of one of the tricky things about stats and this kind of significance testing is, again, we're failing to reject the null hypothesis, right? I said it's not contagious. I assumed yawning was not contagious, and I'm failing to say that that statement is false, right? I cannot say for certainty that yawning is not contagious. Okay, and I know that that's weird. I know it feels odd sometimes reading it and saying it, but that's what we're doing. Okay, because our assumption was that it's not contagious, and I basically can't say that that isn't true. I don't have enough evidence to do that. Okay, so in this case, we have busted those mythbusters who tried to claim that it was contagious, even though we've shown that we don't have enough to say that it is. Okay, so that is that activity. I'm going to do the wrap up, and then I'm also going to do the part underneath. I recommend you stick around for that just because it's going through the same problem, but just kind of wrapping it up and putting it into kind of a review perspective. So you can see the full significance test just kind of laid out directly. Okay, so first of all, our important ideas here. Learning target number 1 was about stating our hypotheses when it comes to a difference in proportions. So when we have this, when we have a difference in proportions, our null hypothesis, so is going to be that P1 minus P2 is 0, right? There is no difference. P1 and P2 are the same. But we could have 3 different alternative hypotheses depending on the problem and kind of depending on what we're trying to prove. So our first alternative hypothesis would be that P1 minus P2 is actually less than 0, which would mean that P1 is less than P2. P1 is the smaller number. We could alternatively say that P1 minus P2 is greater than 0, meaning that the first proportion is bigger than the second one. Or we could say that simply P1 minus P2 is just not equal to 0, right? I don't necessarily know that one is more than the other. All I really care about is, can we prove that they are not the same? Okay, and so we want to make sure that when we do this, we define P1 minus P2 with a direction. Okay, I want to know what P1, what P2 is, and make sure I'm very clear about which one I am subtracting, and then ultimately, right, which one are we looking for? Okay. So that's learning target number 1, our different hypotheses. Learning target number 2, we didn't get into this yet, but this is also important, is our conditions. Right? Are the conditions met to run a significance test? Similar to what we've learned previously, our first condition is that we need it to be random. So we need random samples to generalize to the population, or random assignment, which again allows us to show causation. Our second condition is the 10% condition, which we only need to check when we are sampling without replacement. And to do that, we need to take our sample size of 1 and make sure that it is less than or equal to 1/10 or 10% of our population. And then we also need to do the same thing for our second sample. Make sure that that's less than 1/10 or 10% of the second population. And then third, this is where things get fun, is our large counts condition. And here's what we're going to need to check. This is a little bit different than what we're used to. Same idea, but with some new variables here. So we need sample size 1 times p hat combined, which I'll define in just a second, has to be greater than or equal to 10. And n1 times 1 minus p hat combined also has to be greater than or equal to 10. So that's for the first sample, and then we have to do the same thing for the second sample. Make sure that sample size 2 times p hat combined is greater than or equal to 10, and that sample size 2 times 1 minus p hat combined is also greater than or equal to 10. And again, remember, these are just the number of successes and the number of failures, right? So I need to be able to have at least 10 successes and 10 failures. And so what is this new thing, p hat combined? Okay, our p combined is our sample 1 plus sample 2, actual value we get, not sample size, but the actual value we get from those samples, divided by sample size 1 plus sample size 2. So I'll show you an example of that in the bottom section, okay, of what that means and what that looks like. It's not as complicated as it looks, but it is new, so I will talk about that, okay? So if you need to pause that or take a screenshot, feel free, but I'm going to continue moving into this check for understanding part down at the bottom. So to kind of recap our entire lesson here, okay, so again, they were monitored by hidden camera. 34 of them were given the yawn seed, right? They were walked into the room, somebody yawned in front of them and then walked out. The 16 other ones were just walked in and walked out. So that was the data we got. And so we have this information. We have p hat 1, right, which was the yawners in the yes yawn seed group. So yes yawn seed, yes they yawned, was 10 out of 34, which was 0.29. Our p hat 2 was the ones who yawned in the no yawn seed group. So no yawn seed, yes, they still yawned, which is 4 out of 16. Which is 0.25. And then we just talked about this. We also want a p combined. So what was the combined proportion here? And so here's how it works. We're going to take the 10 and the 4, the actual successes from sample 1 and sample 2. Those are going to make up our numerator. So 10 plus 4 divided by the sample size from both of them. So 34 and 16. 34 plus 16, which is a total of 14 out of 50, which comes out to be 0.28. Okay, so again, I can basically think of the combined number of successes. I had 50 participants. I had 10 in one group, 4 in the other one, so a total of 14 successes out of 50 people, which is 0.28. Okay, so we're going to need that p combined here in a moment. Now, our state, plan, do, and conclude. So to do the first 2 steps of this, we're going to state and plan our parameter. So what are we looking at here? We're looking at P1 minus P2, which is the true difference in proportions of people who would yawn. And we're looking at seed minus no seed. Our hypotheses, so our null hypothesis, was that P1 minus P2 was 0, right? Meaning that yawning is not contagious. And so what would show that it is contagious would be that P1 minus P2 is bigger than 0, right? That the people who were exposed to yawning had a higher proportion. Okay, that's why it's not just E does not equal 0. In this case, we want specifically greater than 0, because I want to show that these people in that first group that were exposed to somebody yawning were more likely to yawn, right? I want their percentage to be higher. So our statistic was our p hat 1 minus our p hat 2, which was our 0.29 minus 0.25, which was our 0.04. And our significance level, we're just going to say alpha is 0.05. Again, unless told otherwise, that's kind of the standard. So the name of this procedure is called a 2-sample, because we took 2 samples, a 2-sample z-test for P1 minus P2, or the difference in proportions. And then we got to check 3 conditions. We got to check if it was random. We got to check if the 10% condition was met. And then last was our large counts. So was it random? In this case, we did use random assignment. So we used random assignment. And what does that mean for us? Is that we can show causation, which is important. I want to show that the yawning was what caused the people to yawn. The exposure to yawning is what caused people to yawn. The 10% condition, in this particular case, There was no sampling here, so we don't need to check this. So don't need to check this, because I didn't take a sample of just the 50 people. And then lastly, our large count. So again, remember, this is where our P combined comes into play. So I've got to check sample size 1 with P combined, and then sample size 2 with P combined. So our sample size 1 was 34 times P combined, which was 0.28. If we multiply that, that's about 9.5. And is that greater than or equal to 10? Unfortunately, no. Okay, we're going to check the rest of them just to see and get some practice here. So the fact that that one fails already kind of screws things up. So we have 1 minus 0.28. If we do that, though, we do get 24.5, which is greater than or equal to 10, which is good news. So that was with sample size 1. Sample size 2 was only 16. So 16 times 0.28, which hopefully you could see that that's going to be a smaller number, just because 16 is less than 34. So in this case, that's only 4.5. And is that greater than or equal to 10? Again, no, it's not. And it's 16 times 1 minus 0.28. Well, that comes out to 11.5, which is greater than or equal to 10. Okay, so at this point, we wouldn't be able to run the rest of this test because our large counts condition has failed. Okay, but we've got to make sure. I just wanted you to keep practicing that, even though technically one of those failing would automatically screw things up. Just the practice of checking all 4 of them. Okay, but we want to make sure all 4 of those is good. Again, that's using our P combined with both sample sizes. But yeah, hopefully that makes some sense. It's kind of a conglomeration of a lot of stuff we've learned so far in the last couple of chapters. But again, hopefully that makes sense. If you have questions, let me know. But otherwise, you have your assignment for 9.3a. And otherwise, I will see you in the next one. Remember to like and subscribe and do all those YouTube-y things to help with the algorithm and to get this page on the map. And I'm just kidding because I'm not trying to be a YouTuber, but it would be fun. So yeah, let me know if you guys have any questions, and I will see you next time.